Alright, let's see if we're behaving. Yeah, looks good. Okay. Alrighty. So, yesterday we talked about octahedral complexes and how crystal field splitting works. We saw that we would end up having two of our d orbitals having higher energy than the others. And so, because just the way that those orbitals tend to align with the points where those ligands would bond. If we want to consider other shapes, we can. We'll talk about square, planar, and tetrahedral. Most things that do square planar geometry tend to have d8 electrons at the end of the day, so that could be something like platinum, platinum 2 plus, or gold 3 plus will be d8 as well. These things typically form square planar complexes. If we consider square planar, which clearly I've drawn as a rectangle because I can't even draw a square. If we take, for example, our gold, put some 4 chlorines around it, we'll make our gold, or tetrachloroaurate 3. Fun. Tetrachloroaurate 3. That's the name of this guy. If we want to kind of look at the patterns here, we're going to have our x and y axes. We'll have our z-axis up as before. Actually, I think I did this as x last time, didn't I? Doesn't matter, they're all the same. So, first off, we can see that x, here let's do xz, which would be between these two, so it would be something like, I don't know, something like that. And the other side, whatever, is not going to be touching the ligands, and YZ, which would be this one and that one, and the other two would also not be touching our ligands. However, if we look at dz squared, we have a little bit of potential problem if that's interacting, just because that donut thing there gets a little bit close to the chlorines. But let's take a look at the other two. Yes, Miss Jersey, we all see you. However, if we look at xy, we can see very clearly that Miss Jersey likes to bork. Okay, sweetie. That these are going to clash pretty badly, right? And I'm sorry, this is x squared minus y squared, the ones that are on the axes. We can see that those will clash really, really badly, can't we? And if we look at xy, that's going to be stuff that goes in the plane like that. XY will also have some problems with the ligands touching the orbitals there. So we're going to see that this splitting pattern is going to be a little bit different. I'm just going to put, instead of D for everything, I'm just going to put XZ and YZ here. We're going to have Z squared be kind of the next one. That's a Z. I'm going to have that XY where they're kind of, this is XY right here. They're kind of in between. And then the highest energy will be x squared minus y squared, which is right along those axes. And that's going to collide with your chlorides right there, then and there. So I'm going to just move this down a little bit. So we actually have different energy levels for all of these. So this kind of clashes the most. And this will clash the least. And in fact, typically your x squared minus y squared is actually quite a bit higher than your xy. And so when you see these D8 complexes, you're going to see if we put in our electrons, we're going to end up filling all the way up to xy, but we're not going to end up putting them into x squared minus y squared. That one just has way too much energy. And as a result, no matter what your ligand is, you're almost always low spin for these, no matter what your ligands are. Just because of that x squared minus y squared lining up exactly with your ligands, it's way too energetically unfavorable to do so. So with your D8 complexes that you'll see, very often you're going to see that these will be low spin complexes, and they're going to fill up 4 of the orbitals and not the x squared minus y squared one. And so this would be, for example, our, does gold 3 plus have D8 electrons? Let's see, is it in group 9? Yeah, it is. Okay, so yes, it has D8 electrons. As a result, we're going to fill it in that way. All right? All right, so these guys, we're just going to assume they'll always be low spin. So they're always going to fill in the orbitals like this. They're not going to touch the x squared minus y squared orbital. As always, this is energy going up, if we were to think of it as a graph. For tetrahedral complexes, again, I'm kind of zooming through these because most things are octahedral, right? So we're going to have our usual 3 on the bottom, 2 on the top kind of idea. Yeah, and we're going to see that tetrahedral will be almost always high spin ones, for sure. So with tetrahedral complexes, these kind of have the ligands in the opposite place. Opposite places, rather. And so when you end up drawing in your orbitals, if you really want, you can go ahead and Google it, see some of these kind of pretty pictures. I'm not even going to try and draw the tetrahedron with the ligands trying to mix there, but suffice it to say you end up getting the opposite to happen. When you're looking at a tetrahedral complex, you end up getting your splitting will end up essentially making your x squared minus y squared and z squared ones now the lower energy ones, and you'll have the the normal 3 orbitals being your higher energy ones, because those now will be the ones that collide. And as we fill these, we're going to see that just experimentally they've seen that is about the splitting energy, half the splitting energy for octahedral for the same ligands. And so we're going to see that as a result, because the splitting energy is often very, very low. Oh, I wrote XC twice. Oh, okay. My bad. The splitting energy, and therefore they're always high spin. So these guys will always be high spin. So let's say we have something, I don't know, with, I don't know, D6. We would fill them up individually and then start pairing them off after. Or D7, we'll say. let's do something with D7, why not? Just to make the bottom ones a little happier there. And so you're going to see that tetrahedral complexes are pretty much always high spin. You're going to end up with unpaired electrons all over the place. I don't think this would actually even make a tetrahedral complex. D7 probably wouldn't, so let's say D5. Yeah. Let's do something D5. Go away. Where you have something completely, all of them unpaired. This thing will be paramagnetic. It's going to be high spin. So pretty much for all your ligands, you're always going to have high spin complexes with tetrahedrons. So we're going to kind of just summarize here for octahedron, or octahedral rather. Oh. We have those those two be the high ones, and then we have, if your spin energy is going to be, or your ligand splitting spin energy, field split. Oh God. I'm sorry. This is splitting energy. This is pairing energy that I'm talking about. Splitting energy here, if it's greater than water, will be you'll end up with a low spin complex. If it's less than water, again, this is a rule of thumb. It's not a hard and fast rule. Water is kind of that middle point in your spectrochemical series of all those ligands. If yours is greater than water, then you'll probably have a low spin complex. If yours is less than water, you'll probably have a high spin complex for octahedrons. For square planar, let's do tetrahedral next because it's just right here. It's the opposite. We're going to just say that those are always high spin. Again, there will always be exceptions, but suffice it to say. And then square plane is kind of the weird one, where we have x squared minus y squared, super high up. We've got xy there, z squared here, and then the other two down here. Nope. Yes, there we go. And these are always low spin, often using D8 electrons, or D8 species. All right, so most of your homework, I think, is on the splitting stuff, so here's your kind of summary. We can do an example. Yeah, the book is one we can do. Actually, this is an octahedral one. It's boring. Let's see what we can do here. Okay, so let's do a problem from the book. This is 23.8. Let's see. Nickel 2 stuff often goes square planar. Can either go either one. It's with a coordination number of 4. We're going to see that we have a couple of these. We have the tetrachloronickelate 2 being paramagnetic. And the tetracyanonickelate 2 is diamagnetic. One of them is square planar, the other is tetrahedral. Let's see which is which. So, if we kind of just draw out the ideas we have for this. For square planar, oh lord, I'm not going to have the room to, oh, but yes I will, okay. If something is square planar, it'll look like that. If it's tetrahedral, it'll look like this. So let's see what's what here. So we have nickel 2 plus. If we find nickel on our periodic table, nickel is 1, 2, 3, 4, 5, 6, 7, 8. So it's got 8 d electrons. It's lost its s electrons, right? We always lose s electrons first. So we have 8 d electrons to fill here. If we fill these both with 8 d electrons, next. Oops. Remember that a square planar complex should always be low spin, and a tetrahedral one should always be high spin. We get these two configurations, right? If we look at these two configurations, well, we see that this one is diamagnetic, everything is paired off. And this one is paramagnetic, right? As we filled those 8 d electrons in here. And so, if we're told that the chlorine one is paramagnetic, well, that one must be tetrahedral then. And if the cyanide one was diamagnetic, then that must be our square planar complex. So again, you can figure out what geometry these things are taking by looking at some of their magnetic properties. So we can see exactly which one's which as a result. Yeah, exactly. So the paramagnetic one will be tetrahedral, and then the other one will be the square planar. All right. So stuff you can do with these. So you have your homework up. It's there. It's not too long. You have, I think, 2 weeks and something to do it. So it's it'll be there for you whenever you feel like getting around to it. I would suggest doing it sooner, not only because this stuff will be fresher in your memory, but also it'll give you more time at the end to prepare for non-transition metal stuff. So, alrighty. Any questions on that? Crystal field theory, fun stuff. Ah, okay. I'll fix that, Kevin. Okay, I'm surprised. Yeah, you probably would have already turned it in otherwise, huh? So I'm going to do that right now. I'm going to copy it over. Any other questions on whatever we're doing? Transition metal stuff? Anything else? Okay, so Kevin, it'll be there in just a sec. It's copying right now. All right, we have one kind of last little bit to talk about, which is something that I kept forgetting, which is chelation. So chelation is, we're going to see a process of moving metals out of other things. So, okay. So Kevin, you should be able to check. It should be up there now. Okay, so the chelation is when something kind of gets removed, effectively removed, we'll say. And so you'll use things called chelating agents to get rid of metals that are in your reaction that you don't want to be there. This is often very important in biology, where you'll have metal ions that you need for certain things, but otherwise they might react with things around them, so you have to kind of keep them separate. So you'll also see these as sequestrating agents. Sequester means to kind of like, kind of like bottle up, keep it in one place where it can't go and do stuff. A very common one is EDTA, which is ethylene diamine tetraacetic acid. And so EDTA looks like this. And if we put all of our lone pairs on, we see we have 4 negative charges here. We're going to see that this actually this is a hexadentate ligand. Obviously with the geometry I've shown, it can't really, but it's actually quite remarkable. So if you imagine the nitrogens coming up from above, and then those 4 acetic acid groups kind of going around, you'll end up getting like a cage on top of your metal. So I'm going to try and draw this. Oh gosh, this is going to be a disaster, but we'll try. Okay, so if you think of your happy, I don't know, nickel or whatever you have going on in here, we're going to see that you can make dative bonds in a nice octahedral manner with just one molecule. So this EDTA can completely bind up all of the octahedral sites on this random nickel. I mean, most metals will behave the same way with EDTA. So it is a chelating agent or a sequestering agent that you can use to kind of block off a metal from being able to react. And so we're going to see that these are often very commonly employed in chemistry. Notice that this EDTA has a 4 minus charge on it. So it is something that is very ionic. It's great for aqueous-based things because it dissolves nicely in water, and you can use it to trap out metals to prevent them from reacting or forming complexes with water or other things. So now it can't react with other things. And so it's effectively been removed from the solution. If we take a look at other things, in organic chemistry, we're going to see there are a group of compounds called crown ethers. That are able to do the same thing, but in yeah. So yeah, you can use phosphates as well. They have plenty of negative charges to interact with other things. You can precipitate things out of detergents that way. Yeah, for sure. Crown ethers are kind of a special case because they're able to interact with these alkali metals, which don't normally form complexes. Where these kind of lines I'm drawing are carbons. And then the one with 6 of them. It's for potassium. these crown ethers actually won the Nobel Prize, I don't know, about 20 years ago or so, because for the longest time they could not sequester alkali metals. Because they typically, if it's on something normal, it'll just go and do its own thing because, they're strong electrolytes are just going to go and be sucked off by the water or whatever. But in organic solution, you don't have something to take off alkali metals because there's no water in organic chemistry that we use. So there's no water to remove your sodium off of something to make it dissolve. But these crown ethers are capable of plucking off these alkali metals and kind of, again, sequestering them, allowing that anion to be free to do whatever you need it to do. So something like sodium borohydride, if you wanted to use this as a reducing agent, you would need to get rid of that sodium so that the borohydride is free to do the reducing. And so you might do that by introducing a crown ether into your solution there to get rid of that sodium for you so you can start dealing with the borohydride. So an example for organic chemistry, I don't think this is even in your book, but it's really cool. And Nobel Prize winning here, just having these simple molecules to get rid of metal ions. So chelation is super, super important. So, all right. We are done with transition metals and this coordination chemistry. Yay! Chemistry, there we go. And so that's going to bring us to our last topic of the semester, which is, in my opinion, the easiest one. And it's going to be the one that's the most different. Because all of the chemistry we've talked about has dealt with electrons, right? We've talked about coordination complexes that use d-electrons, d-electron transitions there. We've talked about electrochemistry, which is electrons moving in between things. We've talked about all sorts of, electron-based chemistry. But now we're going to talk about nuclear chemistry, which is a whole other field that has nothing to do with the chemistry that we've studied so far. We're going to see that nuclear chemistry deals with nuclei, the centers of the atom. We're not going to look at electrons anymore. Now we're looking at the nucleus of the atom. Nuclei are made of nucleons, which are your protons and neutrons. So nucleons is a term that encapsulates both protons and neutrons. Nuclei, of course, just refer to the plural of the nucleus of the atom. So your nuclei are made of nucleons. Very good stuff. So we're going to, of course, do some vocabulary first. Typically, we'll write protons like this and neutrons like this, where just like before, we have your mass number, which was your protons plus neutron, or the number of nucleons you have. Z is your atomic number, which is your number of protons, and then E was your element symbol. So this is kind of a refresher here. So we often will talk about these nucleons as 11p or 10n. 11p, of course, has got one proton plus neutron. It's also got one proton. It's just a proton, so there are no neutrons there. And then the neutron is there. It's a neutron without a proton. So that's how we will describe neutrons there. So just remember that your A up there is your mass number, which is your protons plus neutrons. So just don't forget that. Similar stuff that we've talked about before. We're going to see that many nuclei are stable and many are unstable. And we're going to see that when nuclei are unstable, they will break down. And this will happen in a number of ways. So they can break down spontaneously by themselves, or they can be ready to be broken down by something else. But suffice it to say that when they're unstable, they can break down. If a nucleus is stable, they will not break down. We'll learn to predict the stability of nuclei in a little bit. But suffice it to say, there are a number of ways that nuclei can become more stable. And these processes, or one way that it can do this is through a process called radioactive decay, which is one way to make nuclei stable again. And what you can do is oftentimes we'll talk about 5 different processes that things can go through. We'll have one called alpha decay, or alpha emission. Where you'll have something like, I don't know, what's radon's atomic number? 86. Yes, Miss Jersey. An alpha particle can be released. An alpha particle is the nucleus of a helium atom. So it's an alpha particle. So you might see it written as the nucleus of a helium atom like that. But very often you'll just see it as alpha. How we balance nuclear equations, by the way, is we just look at the mass numbers and the atomic numbers and make sure that they are equal on both sides of the reaction. So if we have released an alpha particle, we're going to end up having our mass number reduced by 4. We want the top numbers to add up to each other in order to be balanced. We want the bottom numbers to also add up together when we balance them. And if we were to look at this, what the hell is element 84? Well, it is polonium. And so this is how something like this can happen, an alpha decay process, where your nucleus for this particular radon isotope will spit out an alpha particle, and it will, as a result, have made its nucleus a little bit smaller. It will have gotten rid of 2 protons and 2 neutrons, thereby making it a little bit smaller. We're going to see that very often large nuclei are the problems. So one way to make your nucleus smaller is to undergo alpha decay, which is something that will release an alpha particle. So every nucleus in your sample will do this. We'll all do it at different times, but they'll spit out an alpha particle producing polonium-218 instead. Alpha decay is mostly done by elements with atomic numbers less than 84. Typically, when we're looking at alpha decay, it's mostly done by things with atomic numbers of 84 or greater. I don't know how to do these greater than. Yes, duh. Something that's 84 or bigger is what's going to undergo alpha decay most likely. We're going to see that there are always exceptions, so smaller nuclei can undergo alpha decay, but typically it's done with larger nuclei. So just to kind of note, before I talk about the next one, for balancing nuclear equations. We just mass number of reactants must equal your mass number of products. When you've added them all up. And then the atomic number for reactants must equal the atomic number of your products. And technically these are sums. So all of your mass numbers must equal all of your mass numbers on the other side. So just keep that in mind. It's really easy to balance these. Just make sure everything on the top equals everything on the top on the other side. Everything on the bottom equals everything on the bottom on the other side. Easy. Another process is beta decay, which will you'll end up releasing beta particles, which are just electrons. These end up being emitted. So something that might undergo beta decay oftentimes you'll see this as beta, so I will keep it as beta. If we want this one to be balanced, well, we need the 40 to be the same on both sides. So currently we have 0. So we'll still have 40 for our mass number. In this case, we have 19 on the left, -1 on the right. So we're going to need 20 then on the right to make them both equal to 19. And that will be calcium. And so we're going to see that overall, I guess we should just, we'll do the overall later. This is an example of beta decay. We're going to see that beta decay these are going to be done by nuclei with too many neutrons. Because if you see what we're doing here is essentially we're going to be converting one of those neutrons into a proton. It converts a neutron to a proton. So we end up having our neutron becoming a proton and losing an electron out of it. So this is expelled from the nucleus. It often just goes straight out of your entire atom. These things are moving at incredibly high energy, and it'll be split off. Just so we know, neutrons are not actually made of protons and electrons put together. That's not what neutrons are. So don't think of them that way, but this is just what happens during the process of beta decay is a neutron will become a proton and an electron, but they're not made of them. So you can't just take a proton and electron, squish them together, and now you have a neutron. It doesn't work like that. So, at least physically speaking. So chemically we might write it as that, but in reality that's not what, don't think of it that way. So just think of it as a process by which we are removing an electron. What about neutron stars? That's physics. Don't know. It's something I'll look into because I at one point, was fascinated by the nuclear processes that are happening in stars. So we can talk about neutron stars tomorrow once I read up on them a little bit. I think they're really cool. All those quasars and fun stuff like that are awesome, but not my realm of expertise, so I'll just leave it at that for now. We can talk about those tomorrow. I think it's cool stuff. Alrighty. So for atoms with too many neutrons, They will end up converting a neutron to a proton, and in the process spit out a beta particle, which is the same as an electron. The last kind of one we'll talk about is going to be, gamma is not really something that we'll talk about. See, we've got positron, we've got, why can't I remember the fifth one? Positron emission, electron capture, and is there a fifth one? Am I just making this up? Let's see, let's check the table of contents. No, there is, I don't know what I'm talking about. There is no other one. So, cool. Those are two ways to do it. We have another two processes we're going to talk about, which are electron capture and positron emission. They're two different processes, but they do the same thing overall. So this would be something that's going to be kind of the opposite of beta decay. You're going to have something that has too few, let's say this one. I'm making this up. I don't know if this isotope actually exists. But if it did, it'd probably be unstable. Actually, no, it would probably be stable, but that's neither here nor there. Okay, anybody, what happens in this process is we end up decreasing our atomic number by 1. Number 18 is argon. Out of it. So this is kind of the opposite process. This is now a proton and an electron transitioning into a neutron. Again, not in reality. In chemistry, that's what happens. So we are effectively getting rid of a proton by converting it to a neutron, and in the process capturing an electron. So we're going to see that these aren't physical processes because there is mass loss associated with these. So the mass of a neutron is not the same as the mass of a proton plus the mass of an electron. So we'll see there is some mass loss here. So we're not going to worry about these. With positron emission, a positron, by the way, is a positive electron. So same size and mass as an electron, but a positive charge instead. It'll get the same job done. What was this? Argon plus a positron. And we very often will include the plus there on the positron, just to indicate that just to make sure that we understand it's a positive electron, so that there's not any like negative that's missing or something. It's specifically positive there. And it does the same thing, essentially speaking. We're taking a neutron, or rather we're taking a proton and splitting it into a neutron and a positron overall. So take that proton, and now it's transitioned into a neutron, and in the process released a positron. So again, these two are the same process, but an electron and a positron are obviously different things. So you can't say that a proton is made of a neutron and a positron either. Doesn't work that way. A neutron is not made of a proton and an electron. A proton is not made of a neutron and a positron. Neither of those scenarios, even though chemically that's what we're saying here. So just keep that in mind. All right, these two, or positron emission, is going to be when you have too few neutrons in your nucleus. So you'll undergo beta decay if you have too many neutrons. You'll undergo electron capture or positron emission if you have too few neutrons. And alpha decay is just for really big nuclei. So just so we know, positron emission is generally for smaller nuclei than electron capture is. However, there's no hard and fast rule for which nuclei will undergo positron emission versus electron capture. So suffice it to say, generally smaller things tend to undergo positron emission instead of electron capture, but that's not always the case. Let's see, I've probably got some, let's see, yeah. Here's one with xenon. In fact, both of these processes happen for xenon. So if we want to write both electron capture and positron emission, two different equations, we can do that. Let's see what happens when this xenon nucleus undergoes these processes. If it undergoes electron capture, we can indicate that by putting 53 on the bottom, which is iodine. Or it can undergo positron emission, and make the same product, that same iodine nucleus or nuclide. So they're the same process, just they are different things. So one thing you're sucking up electrons, the other one you're throwing out positrons. But they get the same task done all the way. They end up decreasing your atomic number by 1. So that's the goal of these two processes. With beta decay, it's to do the opposite. You want to increase your atomic number. But with these two, with electron capture and positron emission, it's to decrease your atomic number. All right? Too few neutrons, so you want to make more neutrons by getting rid of some protons. Positron emission is used extensively in medicine. These are your PET scans, positron emission topography. And what they do is they will put in a radioactive isotope of some nucleus. Typically fluorine is something that's common. 18 fluorine will undergo positron emission. And so we're going to end up with oxygen. No, oxygen is heat. What's oxygen's atomic number? Why can't I remember? No, it is heat. Okay. This positron can be detected as it comes out. So as they put in the fluorine, they can see where the fluorine is accumulating, often in the brain or something like that, whatever organ that you're interested in viewing. You would choose a different isotope based on that. For example, iodine you typically use for measuring the thyroid. Fluorine can be used for the brain. Oftentimes what you'll do is you'll stick this fluorine onto a glucose. And so as that glucose goes to where areas that glucose is being used by your body, like in your brain, it'll emit these positrons. And so you can visualize kind of what areas of the brain are using the most glucose by looking at where the positrons are coming out. And as a result, you can see the brain activity that's taking place there. You can diagnose various diseases using this. So we're going to see that nuclear chemistry is super important in medicine. There's in fact an entire division called nuclear medicine that deals with this sort of thing. So very useful for imaging because you're giving off particles that can be detected. So these particles that can be detected are very useful for localizing things or for viewing activity of things, which can be enormously very useful to medicine. So you can see if you have thyroid cancer and you're wondering if it's metastasized, the thyroid gland is the only really organ that uses iodine in the entire body. So if your thyroid has grown out of control and has metastasized and has sent thyroid cells to other organs as cancer, if you're detecting iodine being used up or iodine isotopes being gathered in an area of the body that's not the thyroid, you can visualize, okay, I see that there's cancer now in your lungs that's from your thyroid. So you have thyroid cancer in your lungs, for example. And therefore they can say, okay, then now we can do some surgery and get rid of it or whatever needs to be done, or targeted your chemotherapy or whatever it is that needs to be done there. You can also give products like these to kill certain cells, radiation therapy, by the fact that these processes are always accompanied by the release of energy. These are all exothermic processes. That extra energy can be used to kill cells. So if that's why chemotherapy makes you so sick, right? You're giving these radioactive substances to patients in the hope that the cancer cells will take up most of them and be destroyed as these nuclei undergo decay. And as these nuclei undergo decay, they're releasing energy. That energy will essentially cook or kill the cancer cells. But because it's hard to kind of target these things, oftentimes the rest of your body also gets partially cooked. So you feel like shit afterwards. So I've never had to undergo this, but that's kind of, it's general knowledge that chemotherapy kind of sucks and that you feel really, really bad, the day after. So, but yeah, that's the idea here. So oftentimes, all of these processes, by the way, they're exothermic. We typically do not write the energy because they're all exothermic, it's all the same. But sometimes you'll see it written with a gamma as well. This is a gamma particle or gamma ray. And this is just energy. So it's a bunch of photons, energy that's coming out, light energy. And so because those don't really change our reaction, we understand it's always going to be in the products. We just typically omit it, but it is there. All right, so just so you know. Alrighty. Well, it's important to kind of talk about, since we're talking about nuclei breaking down when they're unstable, we should kind of consider some factors that make nuclei stable, so we can kind of predict just roughly if a nucleus will be stable or not, or what type of process it's going to undergo. So typically, most nuclei, calcium and smaller, lighter, we'll say, have a neutron to proton ratio of about 1. So, for example, or something like that, where you have 1 proton and 1 neutron, a ratio thereabouts, or very close to 1. I think potassium's is normally 39. That's kind of the most common one, but it's roughly 1. So we're looking at very, very small ratios there. So most things that are at atomic number 20 or below are usually a 1-to-1 ratio. Bismuth is our biggest nucleus that is going to be stable. And it has a neutron to proton ratio of about 1.5. So there's about 1.5 neutrons for every proton in the bismuth nucleus. And so that's kind of where we're going to see that it's not just we can't just say, oh, well, as your neutrons and protons just keep the number the same the whole way. We're going to see that the most stable, larger nuclei tend to have more neutrons than protons. The reason for that, remember that the neutrons are creating the strong nuclear force that prevents protons from repelling one another. And so the more neutrons you have, the more of that force you're able to make. But if you have too much of that force, then bad things happen. So here we go. we're going to see, here's kind of our slope here, that stable nuclei tend to kind of occupy an area that's not quite exponential, but kind of exponential. If we say here, this is 83 protons, there's your bismuth atom right there. Your slope here is about 1.5. Down here, your slope is about 1. In the middle, of course, your slope will be like 1.25 or so. It's about 1.15 where iron is. So you'll see that the stable nuclei tend to kind of follow this. I don't know, what color is this? Kind of a forest green. Most of them will follow along this kind of trajectory. We're going to see that ones that are too far on this side will have too many, or rather too few neutrons, and as a result those will undergo too few neutrons. So we need to convert, no, that's the opposite, that's electron capture, or positron emission. So you have too few neutrons, you need to convert a proton to a neutron, and so you'll do that with electron capture or positron emission. We're going to see this stuff on the other side, stuff over here, have too many neutrons, and so very often they'll undergo beta decay there. And then, of course, stuff that's just bigger than bismuth will undergo alpha decay. So there's not an equation for this. There are always outliers. You know, in reality, it's not a straight line like this. You'll have dots on either side. But these are trends. This is a trend line. So the trend is somewhat exponential, but not quite. And so we'll see that at bismuth, our heaviest stable nucleus, we have about 1.5 neutrons to protons. For smaller nuclei, it's 1 to 1, and then we just kind of increase in between those until we get to 1.5. And once we get bigger than that, things just start going through alpha decay because they're just too big to be stable anymore. Everything above bismuth is radioactive. It'll undergo decay processes. All right. We will, I suppose, finish or continue on this tomorrow. We'll perhaps have a discussion on neutron stars if I remember to read up about them. But perhaps Kevin already knows more than me about that topic, so I have never taken astronomy, so I have no idea. So, cool. Alrighty. I'll see you guys tomorrow. Enjoy the rest of your day.